In the summer heat of 1948, on the quiet, sunlit campus of the California Institute of Technology, something extraordinary unfolded. Inside a lecture hall, funded by a little-known bequest, the Hixon Fund, scientists from across disciplines gathered for what would become one of the most quietly influential meetings in the history of science. It was not a grand conference. There were no press cameras, no awards, no public announcements. And yet, within those walls, the nature of the mind was being reconsidered, not as a soul or a mystery, but as a system, as something physical, as something that could, perhaps, be modeled, simulated, computed. This was the Hixon Symposium. It was here that John von Neumann, a mathematician famed for helping build the atomic bomb and the first modern computers, stood before an audience of biologists, psychologists, and engineers, and asked, "What if the brain doesn't think the way we think it thinks?" His lecture would become legendary. A moment when neurons met logic and minds were reframed in circuits. But von Neumann wasn't the only one reshaping our future that day. Figures like Warren McCulloch, Karl Lashley, and Karl Pribram would bring their own provocations, from neural networks to distributed processing to the first glimpses of what we now call cognitive science. The Hixon Symposium lasted only a week, but it left behind questions we are still trying to answer. How does the brain compute? What counts as a thought? And can a machine ever truly think? This is the story of that meeting, of the people who asked questions too big for their time, and of how a quiet corner of Caltech helped lay the groundwork for modern neuroscience, artificial intelligence, and the digital mind. And special thanks to Matt Phillips 538 for suggesting this topic, a pivotal yet overlooked chapter in the history of minds and machines. In September 1948, Caltech's Hixon Symposium brought together leading minds to explore the mechanisms of behavior, from the neural to the cognitive. Link disciplines as diverse as biology, psychology, and logic. Ask a bold question. Could the brain itself be a kind of machine? The Hixon Fund, established in the mid-1940s, allocated resources for a symposium explicitly dedicated to cerebral mechanisms in behavior under the direction of Lloyd A. Jeffress. Pauling, Jeffress, and other Caltech luminaries envisioned a meeting where neuroscience, physiology, psychology, and emerging computing ideas could cross-pollinate. Held in Pasadena at Caltech, the symposium drew luminaries from multiple fields, including John von Neumann, mathematics, computing; Warren McCulloch, neural network modeling; Karl Lashley, neural basis of behavior; Heinrich Kluver, neurophysiology, cybernetics; Raphael Lorente Deneau, neuroanatomy; Karl Pribram, future cognitive neuroscience pioneer; and others like Ogden Lindsley and Walter Halstead. At the time, behaviorist psychology, focusing on stimulus response, is dominant. But speeches like Lashley's on serial ordering of behavior and von Neumann's automata theories began to challenge this model, suggesting more complex, internally structured processes were needed to explain speech, thought, and sequential behaviors. Von Neumann delivered his foundational lecture, The General and Logical Theory of Automata, on September 20th, 1948, outlining how unreliable neurons could still yield reliable computation through redundancy and error correction. The structural parallels between brains and stored program machines undermining the adequacy of pure Boolean logic for modeling neurobiology. This lecture was later foundational in automata theory and shaped future computing models. Warren McCulloch, echoing his earlier work, emphasized brain-machine analogies. He remarked, "Neurons are cheap and plentiful," suggesting biological networks offered advantages over early, heat-producing electronic computers. This comparative insight deepened discourse on whether brain mechanisms might inspire energy-efficient computing architectures. Psychologists like Pribram and Lashley presented studies on perception, motor planning, and cognitive sequences. Lashley's analysis of serial ordering challenged simplistic behaviorist accounts and laid groundwork for treatment of cognition as information processing, not just reactive behavior. At the heart of the 1948 Hixon Symposium stood the monumental lecture by John von Neumann, titled The General and Logical Theory of Automata, delivered on September 20th at Caltech. It would become a foundational moment in the conceptual merging of brains and machines. Von Neumann began by comparing the structure of neurons with computing machines, noting a vast scale difference. The central nervous system is at least 1,000,000 times larger than the largest artificial automaton, composed of about 103 to 108 elements. Yet he saw promise in modeling brain function via automata theory. Addressing neural unreliability, von Neumann introduced redundancy and error correction as essential mechanisms. Networks of unreliable neurons could nevertheless produce consistent, reliable behavior. This was a radical counterpoint to behaviorist assumptions, signaling that internal structure, not just inputs or output, mattered. Von Neumann described the brain as a collection of black box units communicating via digital pulses, all framed within an axiomatic, formal black box methodology. He also sketched out his early work on cellular automata, universal constructors, and self-replicating machines, connecting computation with biological organization. In a notable aside, he paralleled genes and their copying mechanisms with components of self-reproducing automata, anticipating ideas later found in molecular biology. This interdisciplinary insight foreshadowed his future work on artificial life and replication. Symposium attendees were stirred. The formal automata architecture reshaped their views. Mathematicians and engineers saw a new computing paradigm beyond simple arithmetic. Biologists and psychologists, led by Karl Lashley and Warren McCulloch, sensed a shift toward modeling behavior with structure and redundancy. At the Hixon Symposium, the seeds of what would later become neural network theory and cognitive science began to sprout in earnest. Speakers such as Warren McCulloch, Karl Lashley, and Karl Pribram introduced ideas that bridged biological neuroanatomy and emerging computational metaphors. Warren McCulloch, already famous for his work with Walter Pitts on thresholded neural nets, returned to Hixon to contrast the brain's biological efficiency against bulky electronic machines. He quipped, "Neurons are cheap and plentiful. They operate with comparatively little energy." Von Neumann would be happy to have their like for the same cost in his robot. But it would take Niagara Falls to supply the current and the Niagara River to carry away the heat. By emphasizing energetic and material efficiency, McCulloch set the stage for viewing neural structures as models for compact, powerful computation. Karl Lashley's presentation on the serial organization of behavior argued that tasks like language or complex motor sequences cannot be reduced to simple stimulus-response chains. His findings on mass action and distributed memory indicated that whole brain dynamics, not isolated neurons, govern behavior. This undermined behaviorist orthodoxy and supported holistic or network approaches. Karl Pribram, who contributed empirical work on the limbic system and association cortex, applied neurophysiological data to questions of perception and memory. Though he would become known for his holonomic brain theory later, at Hixon he emphasized that brain function involved distributed, wave-like processes, foreshadowing dynamic models of cognition. As Lashley, McCulloch, and Pribram spoke, a clear pattern emerged. Brains operate via networked distributed structures, not linear logic gates. McCulloch's cheap neurons, Lashley's distributed representation, and Pribram's wave-like processing collectively signaled a pivot toward connectionist views, where cognition is seen as arising through the collective dynamics of networked units. While Rosenblatt's perceptron appeared in 1957, Hixon's neural analogies provided the intellectual soil. The symposium reframed neurons not as unitary stimulus-response relays, but as components of larger adaptive systems capable of learning and pattern recognition, a shift toward analog computation and statistical learning. As the Hixon Symposium progressed, it became clear that something larger was happening. The traditional boundaries between psychology, physiology, and computation were beginning to dissolve. What had started as a symposium on cerebral mechanisms was rapidly evolving into a forum for redefining the human mind through the lens of systems, signals, and symbolic processing. Nowhere was this shift more apparent than in the presentations focused on speech, perception, and behavior. Fields long dominated by behaviorism, but now increasingly open to a new way of thinking. Throughout the early 20th century, psychology had largely followed the behaviorist model. The brain was a black box, and mental life was considered unmeasurable. Only what could be observed, stimulus and response, was treated as scientifically valid. But at Hixon, that view was losing ground. The researchers in attendance weren't just interested in reactions. They were asking how brains interpreted input, how they constructed meaning, how memory and perception emerged from neural structures. Suddenly, internal processes were not only fair game, they were the main attraction. Several speakers introduced the radical idea that cognition might be symbolic, that the brain may manipulate internal representations, codes, or patterns in a way analogous to language or mathematics. This was not idle speculation. These models were being tested, measured, discussed. Whether it was the timing of neural pulses or the architecture of cortical pathways, researchers were treating the brain less like a passive receiver and more like an active interpreter of information. It was here that the first serious bridges were laid between neurophysiology and information theory. Signal transmission to pattern recognition, even early forms of predictive modeling, all were on the table. Some of the most intriguing ideas came from efforts to model visual processing. One common theme was the idea that the brain didn't simply react to images, it actively constructed them. Rather than a camera that records passively, the brain was seen as a predictive, adaptive system. It filtered data, filled in gaps, and assembled a coherent world from incomplete inputs. This idea, though in its infancy, would later explode into entire fields like computational vision and cognitive modeling. It would be hard to overstate just how revolutionary this all was. Many psychologists of the time still believed in a strict behaviorist framework. To talk of internal mental representations was, in some circles, still taboo. But the Hixon Symposium offered a safe space, an intellectual frontier where those ideas could be voiced, debated, and developed. And more importantly, they were being backed by biology. The convergence of neurophysiological evidence with new mathematical and computational tools gave these once theoretical concepts a powerful foundation. As the discussions at Hixon moved deeper into the mechanics of perception and the structure of cognition, a quiet shift was taking place. The mind was beginning to be seen not as a mysterious entity, but as a system. A system that took input, processed it, stored it, recalled it, and adapted over time. For the first time, psychology was being reframed as information science. Thought was no longer a shadow. It was becoming a process. The Hixon Symposium helped launch a psychological revolution. Speech, perception, memory, once the province of speculation, were being reframed as computational problems. By blending neuroscience, psychology, and engineering, the participants began to outline the earliest versions of what would become cognitive science. The behaviorist wall had cracked. Now it was time to ask what would grow through those cracks. The Hixon Symposium of 1948 lasted just a few days. No grand declarations were made. No press releases followed. Yet, over time, those lectures, notes, and quiet debates would echo across decades. Though its impact was not immediately recognized by the broader public, the symposium helped plant the intellectual seeds that would grow into modern neuroscience, artificial intelligence, and cognitive science. John von Neumann's lecture at Hixon would not remain obscure. His reflections on automata, redundancy, and unreliable components were later refined, published, and distributed widely. They shaped not just the architecture of digital computers, but the philosophical framework through which scientists would model brains, machines, and even societies. The idea that a system could be composed of unreliable parts, yet still produce reliable output, became foundational in fields as diverse as computing, communications, fault-tolerant engineering, and even genetics. His insights bridged the mechanical and the biological, and left the door open for something new. Artificial cognition. Less than a decade later, in 1956, a new generation of scientists gathered for the Dartmouth Summer Research Project on artificial intelligence. Many of the foundational questions raised at Hixon about computation, modeling, perception, and the mind would re-emerge there, reframed under the banner of AI. While Hixon had focused on the biological and psychological dimensions of the brain, Dartmouth would take the leap into machines. But the lineage is unmistakable. Without Hixon, the Dartmouth Conference would have lacked both language and precedent. The neural analogies presented by McCulloch and Lashley at Hixon were temporarily eclipsed in the 1960s, as symbolic AI gained dominance. But in the 1980s and beyond, as connectionism and machine learning re-emerged, many researchers returned to the original neural metaphors discussed at Hixon. Today's deep learning models, built upon artificial neural networks, echo McCulloch's early visions of adaptive, parallel systems capable of complex behavior. The intellectual trail leads back to Pasadena. Perhaps the most lasting influence of the Hixon Symposium lies in the birth of cognitive science. It was at Hixon that the mind was first approached explicitly as a system, one that takes input, encodes and stores information, performs operations, and generates output. Psychology was no longer about behavior alone. It was about processing. The field of cognitive science, formally named decades later, took root in the interdisciplinary exchanges that Hixon made possible. Neuroscience, linguistics, psychology, and computation, once siloed disciplines, began speaking a common language. The Hixon Symposium was not loud. There were no newspaper headlines. But in hindsight, it was one of the most important intellectual meetings of the 20th century. It changed how we think about thinking. It helped dissolve the boundary between brain and machine. It introduced the world to the idea that the mind could be modeled, perhaps even replicated, by systems we build. In a quiet room at Caltech, the foundations of digital thought were laid. The Hixon Symposium is not widely known. It doesn't appear in most timelines of artificial intelligence or cognitive science. But in that quiet moment, just 3 years after World War II, at a modest gathering on the Caltech campus, the foundations of a new way of thinking were laid. It was there that John von Neumann challenged the limits of logic, that Warren McCulloch argued for brains as networks, that psychologists began to abandon behaviorism and explore the architecture of the mind, and that the old boundary between neurons and machines began to dissolve. Today, as we build systems that learn, speak, move, and even create, we are, in many ways, continuing the conversation that began at Hixon. A conversation not just about how the brain works, but what it means to understand anything at all. The Hixon Symposium lasted only a few days, but its questions have lasted for generations. And they're still with us, quietly humming beneath every algorithm, every neural net, every attempt to build something that thinks.